Okay, hello everyone. So let's continue our lecture by using this video. And yesterday we talked about the material with any kind of shape under any kind of loading. Okay, and before the loading we draw a cubic like this, and after the loading it behave the cubic element become this shape, this light blue shape. Okay, these light blue shape can be measured with the epsilon x, epsilon y, and gamma xy. Okay, so the example asked us to determine the strength of the element at theta equal to 30, which means that before the loading, the element has this 30-degree orientation, and it becomes after the deformation, it looks like this after we um, substitute all the values in the equations, and then we can obtain the theta equal to 30. It looks like epsilon x1 30 360 times 10 to minus 6, and epsilon y1 90 times 10 to minus 6, and also gamma x1 y1 divided by 2 equal to these equations, and then we can obtain. Finally, we can obtain the red strand element. All right. So yesterday we finished here, and I'm going to continue to the principal strand. Principal strands here. Okay. And because we know the principal strands equation, okay, we obtain this in here, right? Okay, and we set the differentiation equal to 0, and then we can obtain this tangent to theta p, and then we can have the principal strength. And you see that this is really similar to plane stress equations. All right, so we just substitute the values here, epsilon x plus epsilon y, which is the average, right? Plus or minus. Okay, epsilon x minus epsilon y divided by 2, and plus gamma xy divided by 2. Okay, all right, not too good. All right, so 225 times 10 to minus 6 plus or minus 115 times 10 to minus 6 square, and plus 90 times 10 to minus 6 square. We can obtain epsilon 1 equal to 370 times 10 to minus 6, and epsilon 2 is 80 times 10 to minus 6. Okay, maybe you will ask why I know which one is epsilon 1, which one is epsilon 2. Well, the maxima will be the epsilon 1, right? The minima will be the epsilon 2. Okay, the problem now is that which one, the angle, what will it be, right? The corresponding angle, tangent to theta, P equal to gamma xy divided by epsilon x minus epsilon y equal to 0.7826 it leads to theta p equal to 19.0 or 109.0 degree. Okay, so we don't know which one related to each one. So we need to identify it, we need to substitute the angles to the equations. Okay, one of them, and you will know that actually um uh this one, sorry, this one, this is corresponding to the 19. All right. Of course, the other will corresponding to this one. Okay, so actually just substitute this into this equation. All right, and then you can get epsilon x1, and you will obtain exactly the same amount, and then you will connect them. Okay, 19.0 is the epsilon 1 corresponding angle, and of course the other will be 109.0. Okay, so now we are kind of ready to draw the draw the the strain element. Okay, 19 degree, right? 19 degree. It's really kind of flat, right? 19 degrees is not a big angle. So it should be 19.0 degree. Okay, and of course we have a y1 axis. Okay, and we have the original shape. Oh, original shape. Okay, and we will see 370. Okay, it will be 370 times 10 to minus 6. Okay, and the height will be 80 times 10 to minus 6. So you can connecting this line. Hey, stupid. Okay, okay, that's it. So this is the strain element after the principal strain curve. Okay, principal strain orientation. All right, so that's it. And one more thing left is the gamma mix, right? Gamma mix. The gamma mix is, of course, is a maximal shear strength occurred orientations. And good thing is that we know 19.0 and 109.0. So you know that their difference will be 45 degree, right? So remember this 19 and 109.0 in the next page, right? So I'm going to repeat this page, but with the empty space. Now we are going to draw the gamma mix, right? Gamma mix. You know that theta s equal to 19 plus 45 degree and equal to 64. And the other two is 4 equal to 19 degree minus 45 degree. So you got minus 26 degree. Okay, so again, yeah, let's using the Mohr circle for the plane strand quickly. Okay, so you see here. Well, I shouldn't draw this. Okay, because I didn't uh, because I just want to know the angle relationships. So We don't need to draw this small circle exactly, right? So you can see that theta p here, theta p1, theta p1, which is 19, right? And this is theta p2. It's 109, right? 109. So your 64, where is the 64? Of course, it will be in 19. Yeah, you can see that. Of course, it will be theta s equal to 64 degree. Okay, and the other two will be theta s equal to minus 26 degree. Okay, you can see that your theta p1 19 go counterclockwise to 109. So 64 must be in the middle, right? And of course, you go clockwise, you will have negative 26 degree. So you will see that, okay, this minus 26 degree will be theta as 1, okay? Will be the highest. Okay, so if you understand this, we can continue gamma mix divided by 2 equal to epsilon x minus epsilon y divided by 2, 2 plus gamma xy divided by 2. Okay, right. So equal to 146 times 10 to minus 6. Okay, and so you got the gamma mix, right? And you also know the theta 64. Okay, so let's do it. This is 64, right? 64, 64 degree. So this is x1, and this is x, and this is y1. What? And then you have the original shape element like this, and you will have a 146 times 10 to minus 6. All right, um, so you will have the gamma mix divided by 2, right? And 146 times 2, you will have 292. 292. It will be 292 times 10 to minus 6. You know where it is, right? You need to times 2. You can get this, right? Okay, but again, we know that when the gamma mix occurred, we still have the normal strand occur, right? So we haven't done it yet, right? We need to have the epsilon x1. So it will be epsilon x minus epsilon y divided by 2, sorry, plus, and minus, plus epsilon x minus epsilon y divided by 2. And the cosine 2 theta plus gamma xy divided by 2 sine theta. So what is it? Theta. Of course, I will substitute, well, I will substitute 64, right? Actually, you can substitute 64 or minus 26. Both of them are okay, as long as you know where it should be. Okay? So 225 times 10 to minus 6, and epsilon y1 will be epsilon x plus epsilon y minus epsilon x, the strand invariant, 225 times 10 to minus 6. Okay, so now you know that here you will have the length will be 225 times 10 to minus 6. Of course, here will be 225 times 10 to minus 6. All right, so connecting these, you will have the final elements, strand element occurred at the orientation for where the gamma mix occurred. Right. So basically, that's yeah. This is the solution of this questions, solution of this example. Here, one more thing I want to emphasize here for you. Here in the exam, when you are going to draw the strand element with the shear stress, shear strength, you can draw this. So for example, if you have this, okay, so I will give you three equal, I mean, equilibrium uh, way to draw the shear strength. So if you have the strength like 292 times 10 to minus 6, okay? So if you want to draw this, you can either draw like that, or you can draw like this. Okay? Or you can draw like this. All of them are okay. All right. So you can see that you can either distribute your shear strengths all in one side, or you can divide them by two and distribute in both axes. Both are okay. Both are okay. Of course, maybe you will say, it will look exact. I mean, completely different, right? In a real world, it will look like this, all right? But um, because this actually is too tiny in the real world, it's too tiny. So it will even if you distribute both of the distribute into the left hand side or right hand side, they are all okay. All right. So uh, just choose one. Choose the one of the way you feel great to draw it. All right. So that's it. Right. So next is a final topic for the mechanics of material in our department. This is strength measurements. Okay. When I say I remember I said about this strength measurement is close to the experiment or real world, right? So actually, in a real experiment, we typically use strain gauge, okay, strain gauge to measure the normal strain. But actually, it's really difficult for us to determine the angle change, right? The shear strength. We the strain gauge is actually using the uh, electrical resistance. When you change the length of the resistance, it will change its value of the resistance. Okay, so that's how we measure the strength in the normal way. I mean, in the normal direction. We can only it's easier for us to measure the length change rather than the angle change. Okay. However, what we all learn the value about the, you know, epsilon x, epsilon y, and gamma x. So these two are okay, but gamma xy is difficult, right? So uh, we typically using three strain gauges. Okay, and then we are going to use these three strain gauges to obtain gamma xy. Okay, so I will show you how. Okay, so imagine that there's a material like this, all right, material like this, and we stick three strain gauge in X and Y direction and the 45-degree direction. Okay, so we want to use these three known to get the gamma xy. Okay, so how can we get this? It's okay, right? Let's take a look. Epsilon xy equal to epsilon x plus epsilon y divided by 2 plus epsilon x minus epsilon y divided by 2 cosine 2 theta plus gamma xy divided by 2 sine 2 theta. Okay, so you see gamma xy is what we want, right? So you see if you can say at 45 degree, the epsilon x1 equal to epsilon b. That's the thing, right? So all we need to do is write down like epsilon b equal to epsilon a plus epsilon c divided by 2 and plus epsilon a minus epsilon c divided by 2 and cosine 90 degree because this is 45 degree, 45 degree times 2, right? So gamma xy divided by 2 sine 90 degree. Okay, and of course gamma xy. Okay, and gamma xy. So you can obtain this by after the calculation. You have 2 epsilon b minus epsilon a minus epsilon c. Okay, so now you can obtain this gamma xy by using three normal strain gauges. Okay, so epsilon x1 equal to blah 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 blah. You know how to do that, right? Epsilon y1 equal to blah 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 blah, and of course gamma x1 y1. So you see, all you need to do is substitute all these. Okay, so now you have epsilon x, epsilon y, and gamma xy. Okay, so then three any components in different direction you can obtain that. That's good. So I guess you understand what I'm talking about. Okay, so there are some more example I want you to uh, try that at home. Okay, three. For example, if you have a strain gauge A, strain gauge B, sorry, C, it's okay. Your B here, and this is a 45 degree. 45 degree. Okay, so how can we do that? How can we do that? Actually, don't worry. You just need to extend this, and then you will have your 135 degree to obtain this. By using the here at the 45 degree, now it's become 135 degree. All right. Or you can have another possible example. 60, 60, 60. All right. Yeah, or 60. All right. So it will be more complicated, but now you know that you have three known and three known and one equations. So you can always get the value. All right. So I guess that's all for the course. Thank you for your cooperation, and I will see you maybe in other courses. Thank you. Bye bye.